Hello, everyone. Welcome to the Falsifiable Podcast. I am your host, Eric Denton. And today I have a really interesting guest. His name is Robert Hazen. He is a geologist and he has his hand in a lot of other sciences, as we'll hear. Um, and he's the writer of many books, a best-selling writer. Some of those include Science Matters, Achieving Scientific Literacy, The Story of Earth, which is how, or the one that I initially read, and then Symphony in C, Carbon and the Evolution of Almost Everything. And then his newest book, which comes out next year, right at the beginning of next year, is Time's Second Arrow, Evolution, Order, and a New Law of Nature. And he co-wrote this with Michael Wong, and it's great. I was able to read it, and that's what we're going to talk about today. So, anyways, welcome, Robert.
Hey, so great to be with you, Eric.
Okay. And actually, I'd come across you. The reason I know of you is from Nova, and you did one. I don't know when it came out, but I've watched it actually several times because it was fascinating. It's a Life's Rocky Start. When was that recorded?
Yeah, Life's Rocky Start. Oh, that was about 10 years ago, 2014, 2015. I know we did filming in Morocco, we did filming in Australia and in places in the US, and it was really really fun to work with the Nova crew and tell something about the story of Earth and about how minerals have changed through time.
Yeah, that was cool because you conceptualize things. The reason I like how you talk is I'm a big advocate of the work of David Deutsch, and also he is puts out Karl Popper's ideas, which I'm also a huge advocate of Karl Popper. And you talk in the same vein because you uh, science for you, science is about explanations, and I think that that is what the aim of science is, to explain the world, explain reality, and you do that. And in that Life's Rocky Start, that Nova, you conceptualize things as like the Earth starts as black Earth, then it goes to gray Earth, and then it goes, and then you have all these sections, which I thought was really cool because it allows somebody who's not technically savvy or not or adept at all of these subjects to understand it easily. And that's sort of a gift of yours. Do you try to do this all the time whenever you're trying to
Oh
explain
man,
these
I,
things?
I just love telling stories, and we as humans are part of this incredibly grand story, almost 14 billion years of universal history, and then our solar system is, I love the number, 4.567 billion years old. And
Right.
it's been changing and changing and changing, and it still is today, and it always will, and it has been, and it will. And so that's a story. It has an arc, and we're part of that story. And I think we all want to know where we came from and what our universe is like and where it's going and what's
Right.
our future going to be like. Well, the only way you can understand this is, tell the story, and it's kind of a history, and it's really about evolution that has changed through time.
Right. And this evolution, speaking of that, is something that you focus on, and kind of all your work has a through line of evolution, I feel like. And it's kind of apropos because you are a geologist, is that right, Robert?
Yeah, my training was first in mineralogy. That
Okay.
is, these are the solids that make up planets like Earth and the Moon and Mars and other things. And as part of that, then understanding where minerals come from, how they form, you have to understand geology. You have to understand a planet and how it's dynamic, and the oceans and the atmosphere, and in our planet, this thing called plate tectonics and all of the amazing processes, including life. Life has a huge role in all this. And that's where the minerals come from. And so you got to understand all those different domains if you want to sort of tell that story.
Right. And you're like Darwin in this way, because Darwin, he kind of started out mainly as a geologist. I mean, he was sort of an entomologist too, because as a kid, his big thing was collecting bugs and beetles and all
Yeah.
this kind of stuff. But then he met at Cambridge, he met Adam Sedgwick, and that got him into heavily, heavily into geology. And even on the Beagle voyage, he was sort of a geologist more so, but then he
Yeah.
got into more of straight naturalism, looking at the beaks of birds and trying to figure out, like, wait a minute, these things are clearly there's like they're fitting like locks or keys in a lock on these particular islands, and this gave him this idea that he started formulating.
Yeah.
And yeah, so you're like this in this way, and what we're going to talk about today is similar in that you've noticed something like a lock that has a key, and you along with some friends have put together a theory, and it's pretty it's actually bold, and it's this idea of a second law of time. Basically, and you call it, it's actually more particularly, you say it's a law of increasing functional information. Um, and actually in the last in one of the parts of your books, you say, why has this not been thought of before? And I actually have was thinking about this because evolution's similar in this way. There was actually a guy that preceded Darwin that had almost the same idea named Patrick Matthew, who had written something that went in like an art, some obscure magazine for just people who are into trees, and
Yeah.
and he was like, "Oh crap, I already knew that." But to him, it was just like, "Oh, that's just I thought we all knew this." You know what I mean?
Yeah.
And
Yeah. Yeah.
and it was as far as this law of increasing functional information, though, was this how this was to you whenever you came upon it? Were you like, haven't we all sort of thought about this? And also, we should explain what it is.
Yeah. Yeah. So Eric, there is a trend in our lives we see change through time.
Hmm.
And one of those is that every day we get older, we have accidents, we get sick, we slip and fall, we break something. And ultimately, Eric, as everyone realizes, we're all going to eventually die. And when we die, our molecules are going to decay, we're going to go back to dust to dust. Um, and so that's just a trend we know. And we see it in all kinds of things. We see it when you have a brand new pair of shoes or a new briefcase or something. And over the course of weeks and months, it gets scuffed up, it gets aged, it starts to look old. And eventually you say, this is too old, I'm going to throw it out and get a new one. It's also something that happens when you have a hot cup of coffee and you put it on a desk after 30 minutes or an hour, it starts getting cold. And all of these changes are related to each other and they're codified for the last 2 centuries in something called the second law of thermodynamics. It's just a law, the idea that the entropy or the disorder of systems increases. You don't start with a scuffed up briefcase or a scuffed up pair of shoes, and they don't automatically become brand new, clean, and polished. You don't
Hmm.
start up with a cold cup of coffee. It sits there on your desk, and gradually it gets up to the nice temperature that you want it when you're drinking it. And you don't start off, almost, old and sick, and then you gradually get younger and healthier and stronger. That we know that that's not true. So there's an arrow of time.
Hmm.
That is, you start in one state and you get to another state. And in science, the only arrow of time is this increase in entropy, this increase in disorder, the idea that things gradually become more random, more disordered. Because if you start with a very orderly arrangement, a very orderly arrangement is one which is very improbable in this universe. Randomness is much more likely because there are many, many more possible arrangements of atoms and molecules that are random than there are that are highly ordered. So it's just a statistical thing, and people recognized it 200 years ago, and that's the arrow of time, and everybody talks about it. Now, Eric, the thing that's strange and the thing that made me scratch my head, and it turns out hundreds or thousands of other people have felt the same way, and they're all kind of thinking about this independently because they're all contacting us.
Hmm.
We think there's another arrow of time because think about it. You watch your children, they're born, they grow, they learn, they thrive. We look at society and science seems to go from simpler ideas to more complex ideas. We look at the way technology advances, the way, for example, computers have changed over the last 30, 40, 50 years. But also on the longer time scales, language evolution, music evolution. And of course, in biology, you start out with extremely simple forms, the single-celled organisms at the dawn of life, and they've gotten more and more and more complex, multicellular. And now here we are having a podcast where we're talking about these ideas. And
Mm,
so some of us, just some of us, not everyone, it turns out in science, but to some of us, it seems like there's an arrow of time of increasing order or increasing, if you will, a fuzzy word, complexity, or
mm,
maybe increasing information. That when you have more advanced music or more advanced languages or more advanced computers or more advanced life forms, they contain more information.
mm,
Now, there is a whole school of physics that for decades and decades has said, oh yeah, yeah, that's true. But that's just a those are just random sidelights that aren't really important in the universe. That the universe as a whole is getting more disordered. And the fact that there are these little pockets of order, like people, like our brains, like cities, that's just kind of a random statistical thing that once in a while these organized systems, for a brief while, they come into play and then they become much more efficient
mm,
at burning fuel, at dissipating energy, and increasing disorder. You see, because a city, you're using up so much energy, or our brains are using up so much energy, the energy is radiating out into space. And so we're increasing the disorder of the universe faster
mm,
than it would if you took the same molecules that make up our brain and just made them into a soup.
mm.
So they came, yeah, this is all second law. Everything can be explained. The arrow of time, everything we see is due to this increase in disorder. And we thought about this, and we thought about this. And when I say we formed a group about 3 years ago called the Missing Law Group. It was kind of a for fun. And during COVID, we started during COVID, and we sort of met once a week, and we read papers and we thought about ideas. There were three philosophers of science who thought about the philosophy of natural law. We had
Mm,
a theoretical physicist. We had a organic chemist who worked on the origin of life. I'm a mineralogist. We had a data scientist, an information scientist. And so this group was really diverse and coming from all different angles. And we spent 3 years and we hammered out, what do we mean by complexity? What do we mean by time? What do we mean by a natural law? We went through all this. Oh my gosh, we talked about words and what they meant. And, and we kept saying, okay, all the physicists are really smart. So there must just be one arrow of time, right? There has to be one arrow of time. And so we read the paper and they said, yeah, but they kind of they glossed over this point, or they kind of missed that point, or they're not really talking about this thing that we all know is true. And after this 3 year period, we just came to the conclusion, okay, we think they're wrong. We think
mm,
there's a second arrow of time, and it's an arrow of increasing order and increasing complexity. And indeed, we came up with a mathematical description, which we don't need to go into in detail. You can read the paper if you want to, but it's a measure of how complex a system is called functional information. It's information in bits. And our argument is that information in the natural world, measured in bits,
mm,
is absolutely as important as energy and entropy measured in joules or some unit of energy. That these
mhm.
are two complementary and separate things. And people say, "Oh no, no, you're denying the second law of thermodynamics is true." And we're saying, "No, of course not. The second law of thermodynamics is the law. It's always true."
Right.
But just because the second law is true doesn't mean that there might be something that is also true that can't be derived from the second law.
Mm,
Just like
mhm,
gravity is true, right?
mhm.
But you can't derive the second law of thermodynamics from gravity.
Right.
They're
Yeah.
both laws and they're independent and they work together. And what we're saying is there's another law of nature. Now, this is an absolutely audacious, crazy, you know, are you nuts kind of thing. People say, how can you go out? I mean, the laws of nature have been since Isaac Newton, they've been sort of established, they've been set in stone. It's like the Ten Commandments. It's like it's there. And you say, oh, we've got an 11th commandment now. And
Right.
they say, we're not. Well, and so our response is, yeah, we probably are nuts. We're probably crazy for doing this, but we have articulated these ideas in a way that is so intuitively obvious
Mm,
that you're going to have to prove to us that we're wrong.
mm.
And we're not going to say that we're absolutely right. We're going to say we just put the ideas out there. And the way science works, Eric, the way science works is it has to be falsifiable.
Right. Yeah.
And so we've put an idea out there that we think it models all kinds of natural systems, including Darwin,
Mm.
including the way Darwin talked about biological evolution. It fits exactly what he said. It's a little more general. So it applies not just to biology, but it applies to minerals. It
Mm.
applies to atoms. It applies to languages. We've had people now who have written papers in the last year and a half. This just blew our minds. In the last year and a half, there have been more than 100 papers that cited this new idea and used it to apply, for example, how do tumors evolve? It's
Mm.
not Darwinian, but it fits our models. How do languages evolve? It's not Darwinian, but it fits our model. One
Mm.
person wrote an article about how the business use of the internet evolves. It
Mm.
matches our model. I
That
mean,
yeah. Oh yeah, it's wild. I'm curious as to you were just saying there, you said it's not Darwinian, but it matches our model. What why is it not Darwinian in those
okay,
instances?
so Darwin relies
Mm.
on what's called common descent. So
Right.
let's
Okay.
take a step backward. Let's talk about what our model suggests. We say that there's this thing called evolution, and it occurs all over the universe right since the Big Bang.
Mm.
And evolution means an increase in pattern and diversity. You have more different kinds of things, you have more complex things. So let's go right back to the Big Bang and give an example.
Hmm.
All evolving systems have to be made up of lots of little bits and pieces. After the Big Bang, the bits and pieces included things called protons and neutrons. And those are the two particles that make up the nucleus of the atom.
Mm.
Now, right after the Big Bang, the only thing you had were a single proton, that's called hydrogen, or a single hydrogen, excuse me, a single proton linked to a neutron, that's called deuterium. It's another flavor of hydrogen,
Hmm.
and a couple of different ice nuclei that had two protons and one or two different neutrons. That's called helium.
Mm.
Okay, so everything in the universe was hydrogen and helium. That's all there was in terms of atoms. That's elements number one and two on the periodic table. But then what happened is the hydrogen and helium was produced in such abundance that it started to clump together by gravity to make stars.
Mm.
And stars have this amazing thing that when they get large enough, the temperatures and pressures are so great that hydrogen and helium no longer really are stable. They want to start clumping together. So hydrogen and helium clumps together to make carbon and oxygen and nitrogen and all the elements that we have around us. And that's the first generation of stars. You make about a dozen new elements. And then you have a second generation of stars that starts with oxygen and carbon and silicon and a few other elements. And they make a bunch more elements. And then you have a third generation of stars that starts with those elements. It makes even more elements. And you keep it's just like, can you imagine, ratcheting up? You're ratcheting up. You start simple and get more complex.
Right.
So that's the way evolving systems work. They're made of lots of different small bits, in this case, protons and neutrons. They can combine in vast numbers of different ways. You can mix and match just like a chef, with all your different ingredients. And you try lots of different recipes, and only a very, very few recipes work, a
Mm.
tiny fraction. So what we're saying is that tiny fraction gets smaller and smaller and smaller because you're putting more and more and more demands on the system. You have to do things better. You have to make them bigger. You have to make them more complex. And so just as an aside for your mathematically inclined listeners, functional information is the negative log to the base 2 of that fraction.
Mm.
So it's in bits. A negative log to the base 2, 2 means it's the zeros and ones, and it's how many zeros and ones do you need to say, I want something that works this well or is this complex?
Right.
And that number always increases as the system evolves. You ratchet up. My field is mineral evolution. The very first minerals were incredibly simple. They were made of one or two or three different chemical elements, and there are only about 20 different elements that were used. And they were made in stars. Believe it or not, the first mineral, the first crystals that ever formed in the cosmos were in the atmospheres of stars. And a very old star, the atmosphere starts extending and cooling. And when you do that, when you have a little bit extra carbon left over, the carbon condenses to make the mineral diamond, believe it or not,
Mm.
diamond, and then graphite, and then you make a few other minerals. So you start really, really, really simply. Always evolving systems start simply. But once you make diamond and graphite and a handful of other minerals, they can then, when the star explodes, that dust, that stardust gets blown out of the heavens, it starts condensing into planets. And once you have planets, you can start making more minerals. And there are more
Mm.
mineral forming processes. And on Earth, that mineral evolution has now led, we know of more than 6,000 minerals, and we suspect there are about 10,000 in all. So that's
Man.
much, much more complex than the very first. And it's ratcheting again. Life, it turns out, makes about a third of all the minerals that are known on Earth. I mean, no mineralogist ever would have said that 100 years ago. But it turns
Right.
out life
Yeah.
is really important. And so once you get life, then you can start making new minerals. And once you get new minerals, you can start making new life forms. You can
Mm.
start making shells and teeth and bones and stuff. So that there's this co-evolution. And so things just keep ratcheting and they get more and more complex. And what we said, there's the law that says that this just happens spontaneously as long as three things are true, Eric.
Mm.
Three things. You have to have lots of building blocks. They could be protons and neutrons to make atoms. They could be atoms to make minerals. They could be minerals to make rocks. They could be rocks to make planets. I mean, you have to, in biology, you think about you have small molecules and you have cells, and the cells make multicellular organisms. And then the organisms, like you and me, we form a society. So these are all different examples of systems that have lots of interacting parts.
Mm. The reason I ask about so, but it does seem Darwinian in the sense that, what was your definition of Darwinian? Because when I say
Well, it's
Darwinism, oh, go ahead. I'm sorry, Robert. Yeah.
Yeah, it is. Yeah, Darwin's exactly like this. Darwin fits what we say exactly.
Okay.
It's just
Yeah.
we go a little bit farther. So what Darwin said is you have lots of individuals.
Mm.
More individuals are born that can possibly survive, and then you have selection of the fittest. So we
Right.
say that's true. You have to mix up lots of different arrangements of your particles, whether they're atoms or molecules or cells or words in a book or musical notes in a musical composition. You have to mix up those components lots and lots of different ways. And then you have to have a very strong selection mechanism.
Mm.
Some musical melodies are beautiful, some don't make any sense at all. Some
Right.
of words, like I'm trying to make combinations of words that make sense to you. Most combinations of words I might use would be gibberish. They're nonsense. But I'm trying to make words that you will select and say, "Oh, I understand what you're saying." So
Yes.
this and Darwin said the same thing. He said the exact same thing. The only difference is Darwinian evolution requires what's called common descent. That
Mm.
is,
Right.
each
Okay.
individual has to be basically born from the previous generation in a direct descent. And in mineral evolution, in other kinds of evolution of language and words, you can have other kinds of mixing and matching. It isn't common descent. That's a very narrow thing because that means all of your genes have to come from your parents. But in music, for example, you can suddenly think up, oh, I'm going to do something completely different. And I'm going to
Mm.
steal a melody from somebody else. That's not common descent. That's just like what's called lateral transfer. And in
Okay.
in minerals, minerals never they can go extinct if you
Mm.
have some terrible, a huge asteroid hits Earth and the whole Earth becomes molten again. But then the minerals come back again. They
Mm.
don't go extinct forever. But in biology, if a species goes extinct, it's gone. So,
Right.
so there are details of Darwin's evolution which don't apply universally to all evolving systems.
Right.
But Darwin,
Yeah, and
yeah,
in y'all's system though, there is a selection feature which it's selecting for functional information. So
yeah,
it's basically something that works against something that doesn't work, which is
yes,
that's sort of the Darwinian in Daniel Dennett's book, he talks about Darwinism as an algorithm, and basically it keeps what's good and does away with what's bad in simplest
absolutely.
form. Yeah,
It's the
so
same thing. And so in that sense, one of the things we've argued is, or I've commented on, is that maybe, essentially Darwin said it all already, but with
Right.
a caveat that Darwin didn't apply his ideas to mineral evolution or isotope evolution, or certain other systems, non-living systems or technological systems. And but believe me, everything we've done builds on the ideas that Charles Darwin presented in Origin of Species in 1859, and that's the pivotal moment in understanding that evolving systems is a natural process.
Right. And so I would say this too, like the reason I like what you guys are doing and I like this bold idea is A, it does make sense. I think it's actually something I've thought about while in the shower. I've literally thought kind of everything is evolving, and then I'm trying to apply this to different systems. So whenever your book came out, or whenever you sent it to me, I was like, oh, shoot, this is basically what it's kind of what I'm thinking, but this is like you've crystallized it in a way that it makes sense. But the thing I've noticed is that so you're introducing in a way a teleology or a purpose. Have you gotten flack for introducing purpose in the sense that functional information has a purpose and it also
Aha.
it has emergent properties? And do scientists give you flack for that?
So, Eric, this is one of the most interesting aspects of thinking about these ideas with the philosophers.
Yeah.
And let me give you the point. There was a time several hundred years ago when every scientific law was thought teleological. What's
Mm,
the purpose of gravity that Newton described? Well, without gravity, you couldn't have stars and planets.
right.
Without planets, you couldn't have life. And so God made gravity so that it would form stars and planets. But that's not the way we think today. We think, no, this is just a mechanical description of how the universe works. If you have two masses, there's an attractive force between them. And that's just a mathematical equation, and it just describes how the universe is. We think our law is exactly the same. We
Mm,
just said if you have a system with lots of interacting components and you have a selection pressure on that system, some configurations work and some don't.
mm,
And that's just how the universe works. It's not the purpose of the law, it's just the way nature works. Now,
yeah.
on the other hand, if you believe in a creator, and of course many scientists and many other people do, then you look to the natural laws as a manifestation of the creator. And then if you want to take that point and say, yeah, God is great. God created gravity, God created energy, God created the law of increasing functional information. God gave us a universe where we can thrive. I mean, if you want to take it that way, but science is agnostic on that. We simply describe how nature works. It's a
Mm,
mechanism. It's just like clockwork, if you will. You can say, if this, then this. If you have lots of interacting particles and there's a selection pressure, then the system is going to increase in complexity because it gets to a certain state, and then it suddenly can do something new, and then it can do something new on top of that, and it can do something new on top of that. And it's just the way things work. So,
right.
I mean, I'm not going to state what my personal beliefs are in all this because I think that's totally irrelevant. If
Mm,
it's a scientifically accurate and concise and defendable position, then it will just mathematically match what we see in the
right.
universe.
Well, I think it's again, I'm gonna give provide accolades to you and your cohorts because actually, again, it's about explanations, and sometimes you do use reductionist explanations. You don't describe everything quantum mechanically. It doesn't make sense. I mean, you need to describe things. And David Deutsch in his book. It's either the beginning of infinity or the fabric of reality uses a great example in that he says that there's an atom at the tip of the nose of a statue for some Civil War figure, or not, excuse me, not Civil War figure, World War II figure. It might even be Winston Churchill's nose or something in the square of a particular park. And he says to describe why that atom is there, you can't do it by describing quantum mechanics. You're gonna have to use sociology. You're gonna have to talk about war, and you're gonna have to talk about people's feelings and politics and all this kind of stuff to describe why that atom is at that point. So I think it's actually this is what science is about, and people that try to do away with completely do away with purpose and all. I do think you're missing something there or you can be missing something, but you also have to be very careful with it because you do have, religious people or people that are believers in certain religions will capitalize on some of the things that you're saying for their religion. I'm not
Yeah.
against
Yeah.
religions or whatever, but they're going to say, well, he said this and he's a scientist, therefore dot dot dot. And this leads me to the other thing. So we'll talk about this, which is scientists aren't authorities. Nobody is an authority, and this comes from this is sort of a very Popperian view, and all scientists usually think like this. But everything that science does, we're guessing. It's all guesses, in my opinion, and in the opinion of philosophers like Karl Popper. Whenever something is true, it's simply, I use the Alfred Tarski model, which is it corresponds to the facts at that particular moment. So evolution by natural selection has been corresponding to the facts, so on. We still think of it as we think of it as true, but not certainly true. It could be overturned one day. We don't know.
Yes,
We don't,
absolutely. That's part of science. That's
right.
part of
We don't think it will be, but then again, who are we to say? Because we thought that about Newton, and Newton got overturned by Einstein, and we can still use Newton's laws, but like they're an approximation to a bigger framework, if you will.
Absolutely. And Eric, I got to say that that's very much true with us. What we describe is what we call a macroscopic law. That is, this is a law that we experience in our everyday. I look out the window where I'm sitting right now, and I see trees, and I see birds, and I see clouds, and those are levels of organization,
Mm,
which I can describe and understand, and I'm trying to do that. So it's kind of a storytelling, but it's a very educated or informed storytelling,
yeah.
but there's stories that could always be overturned. Now, we say it's macroscopic because we think it applies at the level that you and I experience in everyday life. We don't experience relativity. We don't travel at the speed of light. We don't live near black holes. We don't experience the quantum world except in very indirect ways, with a laser pointer or something. But you can't get down to the level of atoms and see them. And we don't know if our ideas apply at those scales. We just have no idea whether there's a quantum equivalent to this second arrow of time. We have
Mm,
people who are thinking about that, but I'm not a quantum physicist, so I just don't know. I know it applies to, rocks and minerals. I know it applies to living things. I know it applies to the way planets evolve and the way stars evolve. And so those are big systems, big what are called macroscopic systems.
mm,
But there may be no quantum mechanical equivalent to this. We simply don't have that information. And so, yeah, it's just like Newton. He described a macroscopic law of gravity and a macroscopic laws of motion.
mm.
But when you get down to the quantum scale, they don't work. And
Right.
and there are other ways mathematically to describe them. For example, relativistically, if you're talking about black holes or near the speed of light, Newton's laws don't work either. You have to go to Einstein's general relativity.
Mm,
So yeah, it isn't that Newton was wrong. It's just that his laws applied to just the everyday time space milieu that we live in. And I think that for us, that's enough for now,
yeah.
because that's what you and I care about, right, Eric? I mean,
Right.
we don't necessarily worry at night about, gee, what's happening in the quantum realm, but you do worry about
Right.
you worry about your kids,
Hmm.
you worry about what's happening with them. Um, and I think that one of the things that's so amazing about this new idea we're proposing is that it really does suggest ways we can think about our lives. You
Mm,
cannot evolve in your life unless you try new configurations. And then
mm,
you have to have a very clear idea in your mind about what selection criteria you're going to use. Because you can select badly or you can select well. And this is the only way change happens. Change can't happen if no new configurations are tried. If
mm,
everything's exactly the same as it was a year ago or 10 years ago or 20 years ago, there's no evolution possible.
hmm.
But evolution occurs when there are new configurations and they're subjected to selective pressure. And I think that's a pretty profound, it's so simple though, it's so basic. We all know it's true, right? I mean, and that's the thing about the natural laws. Ultimately, all the natural laws, I think, are things because we experience them every day of our lives, and they're just part of the fabric of the cosmos. We just sort of know they're true.
Right.
It's and and then you can build a mathematical framework around it and try to make them predictive and try to make them more important in people's lives. But to me, I'm as I say, I'm just an old storyteller.
Right.
I like telling the stories, and you can you can either fit them into your own experience, or you can say, yeah, my experience doesn't. I don't agree with that.
Right. I actually am I'm one of those people that somebody like Richard Dawkins, who I love, would push against though in the sense that Richard always talks about it's not just a theory, it's a fact, and he's talking about evolution. And I want to push back and say, no, actually it is just a theory. I mean, technically it's not. I mean, but I know what he's doing. He's wanting to push against the people, the creationists and stuff of the world.
Yeah,
But I'm trying to say we can't fight certainty with certainty, though. We need to be epistemologically mature about this and basically say, listen, all of these things that we put forth, even the laws of nature, we follow these laws because we like good explanations, and all of these laws revolve around the reason that they exist is they're good explanations. You can't vary them. In particular, the second law of thermodynamics. That thing is like it's like that old saying of that if your theory doesn't correspond with that theory, you should just throw it out the door. And
that's right.
that's
Absolutely,
usually true. I mean, actually,
it is true.
it's just true. But
Absolutely.
but
In
I would
fact, in
take.
our
Oh, go ahead. I'm sorry, Robert. Yeah, go.
yeah, in our ideas, every time you generate a new configuration, you increase entropy. Anytime you make a selection, you increase entropy.
Mm,
Entropy is always at play, just like gravity is always at play and electromagnetism is always at play. I mean, it has to be. This doesn't in any way, shape, or form call into question or contradict Darwin or contradict the laws of thermodynamics, or anything else. It's just this is a more complete description because Darwin and the laws of thermodynamics and others don't fully describe or explain, much less predict how, non-living systems are going to behave over time, how computer algorithms, how AI might evolve, which
mm,
is a really interesting question, but you can't derive that from the second law of thermodynamics. You
yeah.
simply can't. But people are already at Google. The research division is using, our model to look at how AI is evolving.
Mm,
So because we need to know that. We need to know, well, is AI going to go through one of these transitions where it suddenly can, oh, now AI is thinking, and now the internet is all owned by AI, or I mean, or how do you stop it? How do you basically code in brakes and preventive mechanisms? So people are thinking about this, and you can't use the second law of thermodynamics to do that.
right. I actually think whenever I was reading your book, which again comes out next year, I think everybody should read this book. Also, the book that I originally read by you, The Story of Earth, was just it's like an amazingly clear, fun book to read about how the beginning of Earth and up till now. But this book though is cool because your newest book that's coming out is cool because you do go through all the laws of nature. It's like this really clear picture of where we're at today with everything, and then you introduce this new law basically in the scheme of things, and then you explain what we can do with that, what the purpose might be to it. It's just I liked this book a lot. I'm just going to talk about your writing for 1 second. I liked this because I read a lot of philosophy books that while you're in the middle of it, you'll be thinking, what was this book even about? Like I've lost the thread. Whereas like this book's cool because you're on the thread the whole time. It's just nothing, it's just meat the whole time, which I like. And it's like to the point, whereas you're not going off on all these tangents where I'm suddenly like, this book was about what this is about information or what is this thing? Like it's good in that way, and that's how your book Story of Earth was too, which that's a sign of a good articulator, I would say. I'll just give you that praise. Um, but yeah, I was gonna say something. Whenever I was reading it, though, I started thinking, oh crap, because I'm writing about Popper and Darwin and mixing their theories, and that's been done before too. But whenever I was reading, I was like, "Oh crap! This is kind of treading on some of the ground that I'm covering in the sense that I'm going to have to probably incorporate some of these ideas because I don't know if you're like
Oh,
this, but if
do
you'll
it.
read, yeah, if you read something new and you're like, ah, crud! Now this is introduced into the world. Now this is something I'm going to have to contend with now."
Eric, new configurations. You have to
Right.
keep adding, make the mix wider, make the mix broader, and then you'll come up with your own selection criteria. You'll come up with something new. And that's
That's
what
true.
we hope. Our idea here is just a beginning. And
Right.
if our theory is correct, then this idea will link with other ideas and other configurations, other maybe quantum realm, maybe relativistic realm, or maybe just somebody has a really great idea because the world's expert on the evolution of I don't know, bongo drums. And
Right.
but when I look at the evolution of bongo drum, I see something different, but I can layer that on top of this idea. And so new configurations, new ideas, and then selection. That's how things change. It's almost trivial. I mean, I'm kind of embarrassed in a way because what we came up with in one very real sense is just something that's so intuitively obvious and everybody
Mm,
knows it already that to say this is a natural law, which sounds really
right.
profound and deep. No, it's just hey, you mix things up and you make a selection and then you're gonna be able to do stuff you couldn't do before. That's all we're saying.
Right. And so for me, it compares to what I like to talk about, which is epistemology. Where does knowledge come from? How does knowledge grow? Is it justified? The answer to that last question is no. Scientific knowledge is never justified. Uh, but how it grows, I believe, is Darwinian in the sense that of what you're saying here. It's like you have although it's a little different in the sense that of what I'm talking about is not there are sorts of bad knowledge in the world that grow too, like bad memes that
Are
spread
bad
and
selection.
yeah, and they actually can they're like a sort of a cancer sometimes on society, or they can be like Nazism, I would say, is a prime example of that. Um, and so it's different in this way. Yours is about functional well, let me think here. Even Nazism, there would be functional information technically, but but again, it's just that's bad. I mean, I
Yeah,
suppose.
the subjective part of this, the thing that
Yeah.
makes this so hard for many scientists to accept,
Mm,
is that when you're talking about selection for function, those two
mm,
words sound, oh, that's nice, selection for function. But what do you mean by selection? What are you selecting for? What's the function? When you talk about a individual rock or a crystal. I'm holding a crystal in my hand right now. And what's the function? Well, so it doesn't fall apart. That combination of atoms doesn't evaporate, it doesn't melt, it doesn't transform or weather away to something else right away. So I can keep it on my shelf and it looks pretty a year from now, just like it does today. That's basically the function of a mineral is to persist. And so
mm,
that's pretty straightforward. But when you talk about what's the function of a society,
right.
what's the function of a political system? What's even just getting back to, what's the function of an ecosystem? I mean, is it to preserve the individual cells? Is it to
Mm,
preserve the individual organisms? Is it to preserve the individual species? Is it to preserve the ongoing life of that ecosystem, or is it playing some larger global role? And we really don't have any clear answer to that. So that's a big problem. It's a big challenge to our ideas because when you start applying our law of increasing functional information to the kinds of complex systems that we really want to understand,
mm,
it's not clear how you do it. We don't really know what's being selected for, and we don't really know what the function is
mm,
other than persistence of some sort over a long period of time. But how do you do that? It's mathematically impossible to say what the functional information of an ecosystem is or a functional information of a human brain. I mean, what does that mean? So
right.
we're really at a point where we have a theoretical framework, but we don't have the mathematical sophistication to apply it to the most complex systems, which are arguably the most interesting ones to us. So
Yeah.
that's, if this idea continues to evolve,
Mm.
because new people try new configurations. One of the big things is going to be, very, very high level mathematics looking at systems where are what are called feedbacks, where you change one thing and it changes three other things, and those changes change three other things on top of it. And so you have all these loops of feedbacks, and that's the way complex systems work, and we just don't know how mathematically to treat that. So,
Oh
so Eric,
man.
that's this is selection function. What do we mean in detail? That's a really wide open area of where scientists can criticize us, saying, "Well, you said nice words, but they don't mean anything."
Mm. Yeah, well, honestly, I think that what you guys are doing is cool because you're putting something out there that is objective in the sense that you're putting it out there to be criticized, to be looked at, analyzed. And when scientists put ideas out, they never know what the end result is going to be. It's open-ended for the most part. We don't
Yeah,
it could there's a lot, like as you were saying a moment ago with what I'm up to, there's a lot to be built on here. I mean, we don't really know the cap on any of these things if there even is a cap. There's a okay, so three. I'll ask like three rapid fire questions in the last like 10 minutes here.
yeah.
One, do you? Because I saw in that documentary "Life's Rocky Start." Did you ever get a meteorite from those people in Morocco or a
Oh
piece of
yeah,
one?
yeah, yeah. I got it. I've got it right here in front of me.
Oh man,
It's
that's cool.
very nice. It's a very nice. It weighs about 3 pounds, and it's got a nice fusion crust on it, and it wasn't all that expensive with this one of the really common kinds of meteorites. But oh yeah, I
Okay.
had to have one. It's the oldest thing you can hold in your hand. Eric. This
Right.
is called a chondrite meteorite. It's 4.567 billion years old, and I'm actually holding this object, and it's very much like it was when it formed all
Man,
those years ago. That's really
that's
cool.
yeah, that's interesting. Also, do with the idea of that particular Nova episode. And actually, I think you've been on a couple more too. You were on like a series. I've seen you pop in on some really great ones about planets and stuff.
Yeah,
Um,
yeah.
but what is your theory on the origin of life? Because in that you kind of talk about it, but there is a theory out there that talks about life coming from rocks or from inorganic matter to organic matter. Or what is your theory there? Do you have one?
So actually, that's one of the reasons why we got into this whole idea of the missing law.
Mm.
Very quickly, I think that it's a chemical process.
Hmm.
It involved increasing complexity and kind of ratcheting up. So I think probably because you have to make organic molecules, biomolecules, things like amino acids and things called lipids that make cell membranes and other kinds of molecules. You have to make those, and rocks help you make them through what's called catalysis. And then you have to select and concentrate them, and rocks help you there because the molecules can concentrate on surfaces and be ordered, very organized in new sort of way. Um, and then you just basically have to keep organizing molecules until they learn a new trick. And this is characteristic of all evolving systems. You get to a certain point, and suddenly, oh my gosh, we can do something new. And that new thing, which to me is the key step, not the only step, but the key step in origin of life, is a group of molecules. It might have been 10 or 20, it might have been 100 or 200, making copies of themselves. They
Mm.
started molecule A made B, B made C, C made D, D makes A, and you start using everything else around you as food, and that food feeds into those molecules, and those molecules that make copies of themselves are basically a self-replicating system. Now, they don't, at this early point, I don't think they look much like a living cell today. I think maybe they were actually a coating, a molecular coating on rocks, because rocks have lots of energy. So the
Mm.
rocks can provide the energy to break bonds and put them back together. But I think the molecules had to sort of make copies of themselves. And to me, that's the origin of life. And then it just because our law of increasing functional information is once you have new configurations, then they learn
Oh.
to do new things. They try new things. They arrange molecules in new ways, and off they go.
Oh
That's
man.
the origin of
Okay, you just unlocked something for me. I mean, like a light bulb just now. Yeah, actually, yeah, you talk about this in your book. But yeah, so this does give a purely naturalistic view of the origin of life too, which I think that to me is like for me, I want it to be naturalistic. I truly do.
yeah.
I don't want to have to add like some magical element to it. So that seems Yeah, that's really interesting. So you have this.
That's one of
Yeah.
the things this law does. It just gives, I mean, this is just a natural process that occurs. It's an increasing functional information, increasing complexity, that once you get molecules in a new arrangement, they can suddenly do something new, and then they do something, they mix themselves up and they do something new, and
Right.
then you do something new on top of that. And origin of life is just a sequence of steps of increasing chemical complexity. And
And it's
then Darwin takes over
mm,
at the point when you have genetic information
yeah.
that then that you have to, and actually it's slower. The Darwinian process is slower, I think,
Mm,
than the origin of life process, because Darwin passing genetic information, it means the information is much more rigorously copied. You know it works, but you have all these restrictions. You know, you can't change too many letters at a time. You can't mix things up too much, or the
yeah,
next
yeah.
generation is a mutation that dies out. Um,
Right.
so Darwin is slower than our more general model because common descent puts a huge restriction on how you can do it. But of course, life, you can't mix things up too much because then you just die. You
Yeah.
can't shuffle the molecules
Right.
around.
This also gives that you're giving a challenge to people like creationist philosophers like Stephen Meyer. You're sort of giving a challenge to him as well too, because he still has this idea of, I don't know if you've read any of his books, have you, by just out of
I've
sheer
certainly read the creationist literature, and I feel like uh, they are missing what is a very straightforward, lawful process, and saying, the idea of you find a watch on the by the side of the road, and
right.
it has to have an intelligent designer. They're saying, well, no, I mean the watch is part of a natural evolutionary process
Hmm.
which went through the development of the human brain and then imagining new configurations of gears and so forth, and then a watchmaker made the watch. I mean, that's just part of a natural, but it's the functional information increasing because each time you can do something new, like think
Right.
creatively, imagine possibilities, then instead of having to actually make every single possible configuration to see if it works, you can imagine whether they'd work and you can zero in very quickly. That's what genetic algorithms in computation field do. So it's
Mm,
genetic, last time you flew an airplane or looked at a modern, boat, the hydrodynamics, the aerodynamics, that's all designed by computer because we understand the equations, and the computer can test hundreds of millions of different possible configurations and choose the one that works best. You
yeah.
don't have to make them all. In Darwin, you have to make them and see if,
Yeah. Yeah.
and then if they don't work, you die. And if they do work, you evolve. But a genetic algorithm, you can do a million, 100 million, a billion different configurations in a few seconds.
That's true. Oh man.
So
Okay.
faster
Yeah.
you make configurations and the more rigorous your selection process is, the faster
That's
you evolve.
that's true. And Darwinism works on when we're talking about functional information is a little bit more driven in the sense that Darwin requires random mutations. Does that fall into does that
Yeah, random mutations are trying new configurations.
yeah, yeah,
That you
yeah. Yeah,
I
yeah.
mean, Earth does it. Earth mixes up atoms, stars mix up protons and neutrons. Our brains mix up words and
Mm.
different musical notes,
That's
or,
true. Yeah.
and we try to come up with configurations that work best. And we reject all the ones that don't.
Exactly. Okay.
Oh, I mean, this is just so, Eric, this happens all the time, everywhere, everything you do. You're constantly making choices. Do I cross the street or don't I cross the street? You imagine what happens if you walk into the traffic
Yeah.
and you're going to get hit. So
Right.
you say, no, configuration is we're going to wait for the crossing light. And it may seem trivial, it may seem, almost dumb, but the laws of nature are, in a sense, very, very simple.
That's true. Yeah. Okay, so did you ever see the movie Tenet by Christopher Nolan?
Oh my gosh, I did, but remind me about
It's
it.
the one where the time is they're going forwards in time, but then you have these objects flowing backwards in time, so entropy is actually going in reverse, and they can
Oh,
like they catch bullets instead of shooting bullets and all this kind of stuff.
okay,
Yeah,
okay, yeah, I sort of remember.
yeah.
Yeah,
The
I
reason
love things they're sort of working with that mess up time. You have time travel, or you go forwards and backwards, or you can picture things.
I,
Um,
Did
Yeah.
you
Or
what?
the Tom Cruise movie where he could predict murders before they actually
Oh,
happen.
Minority Report. Yeah.
Minority Report. Yeah, I mean, I love that stuff. I mean, there are violations of what we think are natural laws, but it's great. But the human brain can develop configurations
Mm.
that may not even occur in nature, but we can imagine. That's why science fiction is so much fun because you say, "Oh, wow, now we can think about what ifs."
Yeah. The
And
only
that's
the thing about that Minority Report though, from a standpoint of somebody like David Deutsch or Karl Popper, that actually idea wouldn't work because we do live in a deterministic universe. However, weirdly enough, from what they say, and actually I've been convinced of this. You might find this controversial, but like the actual you can't predict the future because you can't predict the future growth of knowledge. For instance, like we never knew that whenever who was it, Marie Curie figured out that there was radiation coming from a rock. First of all, that was weird. We would have never saw that coming. We also wouldn't have thought that we could run cities from rocks, and
yeah,
like it
yeah.
just this idea that do you find do you see anything wrong with what I just said there, like determinism versus you can't predict the law,
Yeah, no, I
the
mean, one of the great science fiction series was the Foundation series, where Harry
oh yeah,
Seldon was
yeah.
predicting, what's going to happen 500 years from now, and yeah, I think that there's too many potential configurations, and
Yeah.
no human, much less any computer, could look at all the configurations and say which one's going to come true. So this has to do with chance versus necessity, or contingency versus determinism. I
Yeah.
think I think some aspects of selection are deterministic. Some things simply don't work.
Mm.
Some things work extremely well. But there's always going to be the gray areas where things sort of work, or there's different groups of things that work. I mean, there might be 20 different ways to design a bicycle, and the first person who designed a bicycle, might have put a little wheel in front and a giant wheel in back, or a giant wheel in front and a little wheel in back, or two wheels of the same size. They might have used three wheels or four wheels, and then that might have guided for a while.
Mm.
Now, just like with computer code, their whole I'm told by my computer code writing colleagues that there's some idiosyncrasies about computer codes that were kind of locked in early on, and
Right.
those idiosyncrasies are things that if you start it all over again today, let's write the most efficient computer, which you wouldn't have those. And it's the same thing with the 20 amino acids, which are part of every protein in our body. Maybe if you were going to be a chemical engineer and design it, you wouldn't use exactly those 20, but it's locked in. Once it
Mm.
worked, you couldn't get rid of it. So there's all these sort of weird intermediate things where chance may have played a role, but then it worked well enough that you
Right.
build on that. You build on that, and so this is so fascinating. You could spend your whole life just studying what aspects of nature are deterministic versus contingent.
Yeah, yeah. Oh man, yeah, it's super interesting. So we've run up on an hour. Uh my guest today has been Robert Hazen. His new book comes out next year. What you need to do if you're listening to this, just go to Amazon. It's actually for pre-sale right now, and it'll tell you the date. That book is called Time's Second Arrow: Evolution, Order, and a New Law of Nature. It's extremely fascinating. I enjoyed it very much. Super clear for anybody at any level. And yeah, so thank you so much, Robert, for coming on the Falsifiable podcast.
Eric, what fun. Thanks so much.
Yeah,
I really
man.
appreciate it.
I'll talk to you soon. All right, bye.
All the best.